Hi, this is part three of eigenspaces. So we have discussed the definition of an eigenspace being a vector space of Cn, and we review why this set of eigenvectors indeed satisfies the properties required to be a subspace inheriting the addition and scalar multiplication, standard operations of addition and scalar multiplication defined on Cn. The last thing we discussed involved the definition of multiplicity. There is algebraic multiplicity, which involves a power of a factor in the factorization of the characteristic polynomial. And then there is also the dimension of the eigenspace that commonly is referred as geometric multiplicity. So here's another definition. It's called the trace of a matrix, and it consists of the scalar obtained by adding up all the entries that appear on the diagonal of the matrix. Okay, so this is another way of writing A11 added to A22 added to A33 all the way through A sub n. This is what it will be, is known as the trace of the matrix. And we have a matrix that has 2 rows and 2 columns. Then here the trace of this matrix A would be given by the entries on the diagonal, which are A plus D. Okay, so the characteristic polynomial of this matrix is using the variable in the polynomial as variable t. This would be t squared minus capital T plus d, where this capital T is what we're calling here the trace of this matrix, and d is the determinant of this 2 by 2 matrix. So the determinant, this letter D here denotes AD minus CB, the definition of a determinant of a 2 by 2 matrix. So the roots of this characteristic polynomial, this being a coefficient 1, coefficient minus t, and coefficient d, those roots given by the quadratic equation, those roots are then obtained as in terms of both the trace and the determinant of this matrix. So the first eigenvalue is the trace plus square root. This argument of the square root is typically what we call the discriminant. In this case, is t squared minus 4d. This t squared being the square of the trace, and this d being the determinant. This is negative 4 times the determinant. This may be an imaginary number with non-zero imaginary part, a complex number with non-zero imaginary part, or this may be a complex number with zero imaginary part, which is what we would call a purely real number. The important thing is that in general, these eigenvalues are what we call complex conjugates. Okay, they are considered, conjugates of one another. They're complex conjugates. They come in groups of 2, right? And each group of 2, like this, is a conjugate of each other. But there are certain, at least for the 2 by 2, there are certain things that happen that are quite worth mentioning here. And it is that you may remember that if you have the product of 2 things, I don't know, A plus B multiplying A minus B, you multiply this out, you will end up with something that looks like a squared minus b squared. If you don't believe me, you can pause this video right now and you can do the long calculation of this. A times a is squared minus ab, and then b times a, and blah blah blah, right? And so that blah 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 must be equal to a squared b squared. So if we multiply these eigenvalues, we do have an expression that looks like that. Think of t as a, and now think of this portion here as b. So we have something that looks like a plus b and a minus b. And this leads to, precisely by an application of such expression leads to something that looks like the square of the first and the square of the second. But if you square the square root, you end up with this, and we're subtracting it. And by subtracting it, the t-squares disappear, and then we have positive 4d in the numerator, which cancels with the denominator of 4. So the product of the eigenvalues equals the determinant. This here is the determinant of the original 2 by 2 matrix. This is quite a cool result. The determinant of the matrix is equal to the product of the eigenvalues. And now what happens if we add them up? Well, we were saying that they are complex conjugates, something that you could see directly, but one has plus square root and the other one has minus square root. So when you add them up, that portion of the square root, this is going to cancel with this other term, right? And so by adding them up, you end up only with the trace. In fact, 2 times the trace in the numerator divided by the denominator 2. And so the addition of the eigenvalues equals the trace of the matrix. Another important result. And so this example is going to be left as an exercise. In this case, the trace of the matrix would be 0 plus 0 equals 0. And the determinant would be 0 times 0 minus 1 times 1. So this is a minus minus, so this becomes positive 1. So you need to determine what is lambda 1 and lambda 2 in this case. And once you calculate lambda 1 and lambda 2, then you want to do a verification that indeed the product of lambda 1 and lambda 2 equals 1, being the determinant, and that the addition of lambda 1, the eigenvalues lambda 1 and lambda 2, that sum adds up to 0.